Jack, are you a first year or second year student? Second year. I can't remember. Are you taking physics, or are you signing up for Physics 210, or are you intending to major in something else?
As of yet, one of the many things that's going on. I can't sign into the course registration, or I sign in and it doesn't show me anything.
So is it kind of sophomore registration time right now, and the first years haven't registered yet, I assume? Started this morning, okay. Just sort of curious, because I'm always watching the numbers, because we offered 2 sections of Physics 210, and if they're collapsible into one, they will be collapsed, but I'm hoping they don't get collapsed. That would be kind of small enrollment numbers, but it's almost all first years who are enrolling, so you have to kind of wait till the end to really know which way the wind blows. That sounds like Everett's now out for the rest of the semester, which I guess it's a good time to be cut out by contact tracing, because you've only got a couple of days before you go home anyways. You don't want to take it back home, is that what you're saying? Yeah. Is that how the college, that's what the college is doing for anyone who tests positive right at the end? Yeah. Yeah, because I know at some point, wasn't the hotel filled up, and or at least as many rooms as were set aside for center people, and so they were like starting to send people home. I thought that's what President Moreland said at some point. But yes, that, you know, at least if you if you test positive, for sure, but if you test negative and it's been a week, you've tested negative twice, I'd probably just go for it and go home rather than sitting in a dorm alone. But I don't know what the college's policy is on that. Okay, it looks like it's time to start. I have a sort of a bunch of announcements associated with the end of the course and just describing what's coming up in the coming couple of days. But I thought today would be a good day, given that we have presentations tomorrow and then our final next week, to just express my gratitude and how excited I am for the class and how well everyone did in here. It's not an easy lift, and it's not a typical kind of student who signs up for this kind of course. So you should really be proud of yourselves. And I'm, this is the kind of student who really makes Center College a great place. So thank you for all your efforts this term. You've also gotten a chance to see the different styles, really, of physics and philosophy. I mean, they're quite strikingly different. And I know I've told Dr. Kadavid this when I was an undergrad physics major. I took a fair number of philosophy courses, but I definitely wasn't a philosophy major. And I remember probably the second philosophy course I took, I was in office hours at the philosophy professor's office and asked him, why don't they just make one good textbook that has all the best philosophy results in it? Kind of like when you take an introductory physics course, you have the one textbook, they're all kind of the same. They have the best results. The ones that aren't any good, we left them out. And as you've seen, in philosophy, the opinion is totally different. And even ancient views can inform like our understanding of how to think about things now. So, but that was my that was my kind of naive view of things at the time. Okay, so tomorrow we've got our final paradox presentations. Just for simplicity, we'll take them in the same order as we had before. Sorry if you don't like your position, but that's probably just the simplest thing to do. For those of you who are on Zoom, I will try to remember to email a Word document that includes that evaluation form so it's easier for you to fill out and then attach and send back to me. And we can talk about those at the beginning of the presentations tomorrow. Tuesday, my memory is that our final is 8:30 to 11:30. Is that what you guys understand? Okay, always triple check the schedule. It will be in this room. It covers chapters 1 through 17. So it's basically comprehensive on the stuff through the exam we took yesterday. And by the way, I have the exam. I rushed to grade it yesterday afternoon since we didn't have a meeting of Professor Kadavid's class. So I'll hand that back at the end of today. You guys did a really great job. So that made my grading job quite easy as well. And it was not easy material either. All those, you have to really pay attention to details when you're sketching those space-time Minkowski diagrams. So several people, at least expressed some interest in finding a time for office hours on Monday in case you have questions before our Tuesday final. I believe, I'm not sure how Professor Kadavid is using her time, but I think her time slot corresponding to her class is Monday afternoon, if I remember correctly. But I didn't see any definite conflict in Monday morning, at least for everyone. So I'm hoping, we don't have a reserved room, but I'm hoping, I've asked my colleagues if we could use the same lab room that we used for the video game that we played. That's Young 131. And I will email this out, but maybe 10:30 a.m. with the idea that if you're going to come at the beginning, because when no one's there, I'll probably pack up and leave. And I'll open a Zoom session. So if you want to check in on Zoom, you can just ask your questions via Zoom. Any questions or other housekeeping stuff before we begin and hopefully end with our last topic, E equals mc squared, which we just set up of sort of a mystery last time. Last time being Tuesday. Okay, let me share my screen then. This was one of those topics where, let's see if I do slideshow. I just wasn't really sure if I could possibly do it in one day, and we'll see if I succeed in it. But, there's some things justifications that need to be left out, which is probably fine by you guys, but that you might understand if you take an introductory physics course. So where we left things on Tuesday was this weird situation where we at least looked at a carbon-12 atom. That means it has 12 protons plus neutrons. Carbon, by definition, has 6 protons. So that means it has 6 neutrons if we're talking about the isotope carbon-12. And in this strange unit, which really is the size of that unit is defined by the mass of a neutral carbon-12 atom. So it's got 6 protons, 6 neutrons, and then 6 electrons to make it neutral. Its mass, by definition, is 12.000000, exactly 12, in units of U, atomic mass units. Now, In those same units, we can pull apart this atom into its constituent 6 protons, 6 neutrons, and 6 electrons and add up the individual masses. Those masses can be experimentally determined. And the mass doesn't agree. And that's sort of weird. We imagine that, I've got something built out of those pieces, and when I pull apart the pieces, I end up with more mass if I add up the masses of the individual pieces. Newton wouldn't know what to do with this, and that's the whole point here. We're going to go beyond Newton to kind of figure out how to think about it. And to think about it, we need to know a little bit about some important quantities that appear. I mean, it has, E equals mc squared has to do with energy. So we kind of need to understand a little bit about energy. And normally that takes a while to digest in an introductory physics course, but we're going to sort of breeze through it. Merman doesn't breeze through it quite so fast, but it's also sort of a confusing chapter if anybody read it. So let's imagine a particle. So we're going to first talk about the non-relativistic case. In other words, some definitions associated that Newton would have given. In fact, you'll find some of these definitions given in the excerpts that we saw in the book we read earlier in the semester, but they sometimes have different names. So here's a particle of a certain mass m, and it's moving through space, moving in that direction, okay? One quantity, so we're going to try to describe its motion. And one quantity that describes the motion, we've used this word before, is the velocity. Now, velocity is something that physicists call a vector. So the velocity includes the information about how fast it's going. That's what we would call the magnitude of the velocity, but also the direction. So think of the velocity as how fast something is going and also specifying which direction it's moving in. So the direction is shown by this little arrow there. But there are other descriptions of the state of motion of this particle. One of them is called the kinetic energy, and the kinetic energy is related to the speed by, it's just 1/2 times the mass times the speed squared. And there's something called the momentum. And the momentum is also a vector. In other words, it has a magnitude and a direction, and you just get it by multiplying the mass of the particle times its velocity vector. Okay. Seems kind of excessive to have those 3 descriptions, but if you go back and look at the readings we did of Newton, you'll find that he calls this thing in his, what were those? Were those excerpts from the Principia? I guess they were. Calls this the quantity of motion. But if you think about the words he's using, he's really talking about what we call momentum in modern terms. So we've got 3 different things that all depend on the speed of the particle. And the question you might ask is, well, the momentum and the kinetic energy seems very closely related to the velocity and the magnitude of the velocity, which is, we just call the speed of the particle. So why do we even need the momentum and the kinetic energy? In other words, what are they useful for? And one answer that Merman in the last chapter develops quite extensively is in collisions between particles. So again, we're going to consider the case that Newton would have appreciated here, non-relativistic collisions. So these are cases where the speeds are relatively low compared to the speed of light. And the idea is I've got, in this picture, I've got 2 particles colliding, but in general, we could throw 5 particles at each other and they have some big complicated collision and they end up going off in their 5 separate directions afterwards. In those cases, it's kind of useful if you want to know how they end up in the final state, in other words, which directions they're going and how fast they're going. Using the momentum and the kinetic energy, we can figure out things about the final state just by knowing how they came into the collision. Okay, so there's what we call conservation laws for the collision, which says when something is conserved, in this case, I'm talking about momentum here, it means that the same quantity computed before they collided is equal to the same quantity after it collides. So in this case, if we have 2 particles colliding, they each have their own momentum, which is almost the same as the velocity, but it's got the mass mixed in there. And if we add up the momenta before the collision, we'll find that the sum of the momentum of the particles after the collision is exactly the same. That helps us figure out how things are going to be moving. It doesn't tell us exactly how they're going to move afterwards, but it's going to help. Same thing with kinetic energy. Part of the reason we're interested in kinetic energy is that, in many collisions, they're called elastic collisions, but especially collisions down at the, microscopic scale, down at the molecular kind of level, almost all collisions, or collisions that look like this, where the particles keep their identity before and after, conserve kinetic energy. So if we add the kinetic energies of all the particles before they're close to each other, and then we let them collide and they start going away from each other, we add their kinetic energies afterwards, it would be the same. And that also tells us something about how fast they're going afterwards if we knew how fast they were going before. So that's more information. Now, this third conservation principle, and all of these come straight out of Newton's laws. So if you take an introductory physics course, you'll figure out how to derive these. It's in all the introductory textbooks, how to show that this is true from F equals ma, you know, and Newton's third law. Conservation of mass. Now, Newton wouldn't have even thought to remark on this, but for us, this is going to be important. The sum, we've seen masses sort of changing as you pull something apart into its constituents, but Newton, in the non-relativistic case, certainly believed that even if the particles somehow came together and stuck to each other, so there wasn't as many particles in the final state because there was particles composed out of things, that the sum of the initial particle masses should be the same as the sum of the final particle masses, right? Newton wouldn't have even thought to question that. Okay, now all of those quantities, the velocity, momentum, and kinetic energy, depend on the IRF you're viewing them from. Of course, Newton even understands that, right? If you change your IRF, your velocity changes. That means your kinetic energy, which depends on the velocity, changes. Same with the momentum. In this chapter, which I didn't require you to read, and in an introductory textbook, you could easily show that if momentum and kinetic energy are conserved in one inertial reference frame, then even though they have different values, they're going to be conserved in all inertial reference frames. And that means that if they're useful for one person watching a collision, they're useful for everyone, no matter how they're watching the collision. Okay? And of course, the same is true for mass. If mass is conserved in one frame, it's going to be conserved in the other one. Now, what happens or what changes when we go to the relativistic case? Well, there's some disappointments initially. In the relativistic world, if we use the same definitions that Newton gives us for momentum and kinetic energy, you can show easily that if they're conserved in one inertial reference frame, they're not going to be conserved in any other inertial reference frame. And that is, well, it's at least making them not so useful. It seems like those quantities aren't so useful. And we would like to have a collection of useful quantities that are conserved from before and after a collision. And so it seems to suggest that we should look for some new definitions. In other words, maybe 1/2 mv squared isn't quite the correct definition for kinetic energy. And maybe m times v isn't the correct definition for momentum. And if we had a slightly altered definition, then they would be conserved in all inertial reference frames. Okay, so if you read chapter 18, this takes a long time for Merman to work out, and it's very, at least in my opinion, it's sort of a confusing part of that chapter. Here's another guiding principle for looking for what these altered definitions should be. The new definitions, it seems like when the speeds are really small, they better reduce to the old definition. So if Newton believes kinetic energy is 1/2 mv squared, then if we give a new definition that's valid for really high speeds, then when the speed is really small, it should be really close to 1/2 mv squared. So those are some guiding principles that we can hope to use to get some new definitions. Now, we've been talking about energy, and so far we've just talked about kinetic energy. Kinetic energy, the faster something's going, has the definition for Newton, 1/2 mv squared. The faster something's going, the more kinetic energy it has. The more mass, the more kinetic energy it has at a certain speed. But there are other kinds of energy, and the most important kind of other energy is called potential energy. Potential energy is energy that's stored in forces. Maybe the best way to do this is without holding something up. But if I imagine 2 electrons, people probably have the idea that you've heard that if you have things of like electric charge, they repel each other. Whereas if they have opposite electric charges, they attract each other. So if I have 2 electrons and I shoot them at each other, so qualitatively, it would look like this. They're coming in really fast and they go zoom apart like that, right? They don't really actually smack into each other, but when the force gets big enough, they're momentarily stopped and they kind of reverse directives, or maybe they careen off of each other like that. Well, we can see that kinetic energy is not going to be conserved all the way through, right? They had a lot of kinetic energy coming in, and let's imagine they're shot with equal and opposite velocities, same speeds, opposite direction, and they go At some instant, they've come to rest. And when they come to rest, their kinetic energies are zero. And so it certainly isn't true that kinetic energy is conserved from when they're far away to this point where they've momentarily come to rest. And then we get that sort of kinetic energy back when they pull apart again. That kinetic energy isn't really lost. We think of it as stored in the force. And sometimes it's easier to think of, a force storing energy if you picture a force as a spring. So here's, I can think of, well, let's imagine this spring actually doesn't want to compress. It actually isn't very easy to compress this one because it's coiled so tightly. But you can imagine its relaxed state is like this. And I have to really work to compress it, right? That's like I'm visualizing the force between these two electrons that I've got on the edges here, right? So as the electrons lose kinetic energy, they're compressing the spring. It's an invisible spring for that electric force, but they're compressing the spring. And the lost kinetic energy, we say, is stored in potential energy in the spring force, or actually in the electric force. It's an invisible spring for those. We call it potential energy because if you let them go, you can regain the kinetic energy by letting that force sort of undo itself and they get pushed apart. So that repulsion that absorbs the kinetic energy then allows the kinetic energy to be gotten back again. That's why it's called potential energy. It's the same thing with, the Earth's gravitational field. Let me see if I have a smaller mass here. I thought I brought one. There's an attraction between this little brass mass and Earth. And there's an invisible force. But sometimes it's nice to think of it as almost like a spring. There's a spring that's stretched right now, and it really wants to decompress and pull this thing down. Now I can stretch that spring up by pushing against this mass, right? I'm actually forcing the invisible spring to stretch. And when I stretch out a spring, I'm putting potential energy into it because I can get kinetic energy back by letting it snap together, right? Same thing here, right? I stretch the spring up. If I let the spring snap back, we get some kinetic energy out of it, right? Uh-oh, it went somewhere and I didn't see. I've got to remember to get that mass. Oh, thanks. Okay, so we've also got potential energy to think about, and this is going to be important for us. So the idea of potential energy is it's a different way where energy is stored in a force, but it can be released as kinetic energy later, okay? So, even for Newton, this isn't something that has to do with relativistic cases. We only expect the total energy to be conserved between all moments of a collision. In other words, if you go when they're far apart to the point where they're momentarily at rest, clearly kinetic energy is not conserved. But what is conserved is the kinetic energy plus the potential energy, and we would call that the total energy. If the kinetic energy all disappears, then the potential energy is going to go up by the same amount. And as the potential energy goes down, as the spring decompresses, the kinetic energy is going to go up by the same amount. So if you take the sum of those two, we would call that the total energy. That's the E for our mc squared kind of thing, right? Total energy. Okay, now skipping over a lot of the work that Merman does in the chapter that I didn't make you read. Here is the relativistic definitions he comes up with, and these are Einstein's definitions for what the relativistic definition of momentum is. Here's a new definition, and the idea is this definition was chosen so that momentum would be conserved in all reference frames if it's conserved in one reference frame, and it reduces to the old definition. Remember, the old definition, according to Newton, was just P equals mv. M is the mass of the particle here, m0. We'll talk about that in a second, what the zero means. The gamma, remember, when things are non-relativistic, if the speed of the particle, if this v is really small compared to c, gamma is approximately 1. So the momentum just reduces to mv. It's very close to just mv there. Okay, the total energy, which is going to be, well, we'll talk about where the energy is going to be stored there. But the total energy has kind of a confusing formula that's not easy to see how it corresponds to what is in the non-relativistic case. But it's gamma times the mass of a particle times c squared. So as the particle is moving faster and faster, that gamma is going to get bigger and bigger. And m, oops, not sure what happened there. That m is the mass of the particle, Why the c squared is in there is at least not clear right now. The particle's rest mass is given the name m0 in this case. That's the mass that Newton would assign. And at least in chapter 18, some people don't talk about like this, but there's a relativistic mass or inertial mass, which is gamma times m0, which means when something that has a certain mass is moving by you really quickly, it behaves in all respects like it has more mass. In other words, it's harder to accelerate it. If you hit it with a hammer, it doesn't change its direction quite as much because it's acting like it's really massive, right? But in any case, when gamma is close to 1, if the speed is really small compared to c, this is approximately just the rest mass. And then finally, the kinetic energy. This is a really weird formula, but the kinetic energy is gamma minus 1 times m0 c squared. Okay, so that means, remember, gamma times m0 c squared is the total energy. That was this definition up here. So the total energy is the kinetic energy of just a particle moving along, plus this individual energy there. So it says, even if a particle doesn't have kinetic energy, it still has some overall energy. And what we're going to think about is, what does that energy mean? Okay, so the advantages of these definitions is that they reduce to the relativistic ones when v is much less than c. Some of these are obvious in that case. In some cases, you really have to think about how that works. The fact that this formula right here reduces to 1/2 mv squared is not at all obvious. Or I guess it reduces to 1/2 mv squared plus m0 c squared. That's what it's saying. In other words, it gives the old kinetic energy formula back. But we're just going to pass right by that without talking about it. You'd have to do like a Taylor expansion if you know some calculus and keep only the first 2 terms of the Taylor expansion. Okay, so what's conserved in collisions and decays? A decay is a kind of collision, right? I mean, we can think of one kind of collision is where particles bounce off of each other, but another kind of collision might be, just to get in front of the camera here, where 2 particles come together and somehow they stick together and they become one. And the reverse of that is when I have a particle that's one, but it breaks apart into 2 pieces. We might call that like a nuclear decay or something like that, right? Something that was one breaks into 2 pieces later on. Maybe it was kind of unstable and those 2 pieces wanted to get apart and they finally got enough energy and they bounced around the right way and they unhooked something and they were able to fly apart. Okay, so collisions between microscopic particles and decays of microscopic particles. We already said in the non-relativistic case, momentum, mass are conserved. Kinetic energy is conserved if you only go from way before they started interacting to way after, not if you include when the kinetic energy might have been converted to potential energy. The interesting thing here is that what happens in the relativistic case? It's not the same things that are conserved. Mass is not conserved. Kinetic energy is also not conserved. But the important and interesting thing here, momentum, energy are still conserved in all inertial reference frames, but mass, that I'm trying to show in red there, mass is not conserved. That sounds like our mystery that we were addressing in the table of the nuclides that we looked at earlier, where the carbon, the sum of the parts was greater than the mass of the whole. Okay, so let's look at this formula. E equals gamma mc squared. That's what we said. This is the definition of the total energy. We're thinking of it as potential plus kinetic, but we're going to find out there's something else to it, right? Because even if we have an isolated particle and it's sitting at rest, so it has no kinetic energy, and if it's sitting at rest and it's isolated, there's nothing
like
else.
right now, like right now. I mean, I'm in class with Jim. Then
Sorry,
I need to finish my class.
Eva, I'm hearing you
12:45 to 2:15 and
on
from
the
2:30 to 3:30.
Would it be possible, like, this afternoon?
Yeah, I am sharing the screen. In any case,
have a socially distanced.
so what this is saying is when a particle is, an isolated particle is totally at rest, gamma is equal to 1 and E is equal to mc squared. So that means that when a particle is at rest, it has some energy by itself. How are we to understand that? Well, first of all, it suggests that
Okay.
there's an awful lot of energy.
Okay, and
So
my
I'm
kids
imagining
are
I just
having
have an
meltdowns.
isolated electron or an isolated proton or something like that.
Okay.
It's sitting at rest. There's a huge amount of energy.
Remember that I
Let's imagine I have a particle
the one that's
you know,
broken. So there's one
maybe
in
just to
one.
put
Okay.
things in easy numbers, but mass is measured in kilograms. Let's imagine we have a mass of 1 kilogram. 1 kilogram is probably like the mass of 2 cans of Coke or something like that. This thing right here, it's not too hefty. I think this is a half a kilogram or something like that, but it's about 2 cans of Coke mass, roughly speaking. If you have a mass of 1 kilogram, I'm multiplying by something that in normal SI units is huge. C is 3 times 10 to the 8th, and we're squaring it. So that's giving us 9 times 10 to the 16. So if the mass in usual units is 1 kilogram, that's perfectly ordinary mass we might have sitting around. There's like 9 times 10 to the 16th energy units. Those are joules, but you don't need to worry about that. And that's an awful lot of energy, right? 10 to the 16 joules could power the Earth for a long time of all of our energy needs of everyone on Earth. Okay, so there's a huge amount of energy sitting in just 1 kilogram of mass. So that's one meaning of it, but the question is, what can we do with it? You know, if there's no way to use that to power something, then it's just sort of a curiosity, but not really useful. Uh-oh. Have I lost contact because I pressed my laser pointer for too long? Let's hope not. There we go. Okay, so beyond saying mass has energy, what's it good for? Can we transform it into kinetic energy? In other words, maybe we can think of it like potential energy. If we can get some of it out and make things move, we could turn a turbine, do some work, power the lights in the house and that kind of stuff. Okay, so we've got to investigate what rest mass means. Let's imagine we're going to find out that what rest mass we assign to a particle kind of depends on our perspective. So let's imagine I've got some small little particle just sitting here, completely at rest, so it has no kinetic energy right now. And as far as I'm concerned, it's so small, it looks like a point particle. But then I come in with a microscope and I investigate it really closely. Okay, so this, we would say, if it has rest mass m0, then according to Einstein, the gamma is 1, so E equals gamma mc squared just tells us it has energy mc squared in there. But now I'm going to come along with a microscope and look at it really closely. And when I look at it really closely, I find some structure that I couldn't see when I wasn't looking closely. Now, this is just a made-up example, but it might help you think of nuclear decays here. Let's suppose I look really closely and I say, oh, what I thought was just a single point particle, if I look really closely, there's actually 2 particles. They have their own rest masses, okay? And they're connected by some force, which I'm displaying as a spring here. It doesn't have to be a real spring. It could be, you know, a repulsive force like the electric force or something like that. And there's a little clip here holding it together. So that spring is held in a condition where it's completely compressed there, okay? When I now look at this new view that I have at the microscopic level and reassess what the total energy is, I would say, well, now I would say the rest mass is this mass here, plus this mass over here, plus whatever potential energy is stored in that spring. The spring is compressed, so I could get some useful energy out of it. And so Einstein is going to say the same total amount of energy is present in both these cases. Whether I look at it at this coarse-grained level or the fine-grained sort of microscopic level, the E is the same. But in one case, I just think of it all having to do with energy associated with rest mass. And in the other case, I have 2 different rest masses plus some potential energy. And the idea is, if these energies are the same, the sum of these 2 rest masses has got to be less than this original rest mass, because, you know, the sum of these 3 things has to add up to the same thing. So the sum of the rest masses is going to be less than the rest mass there. And so when I look at it in this way, I would say, oh, I thought there was a lot of rest mass, but now when I look microscopically, I find out, oh, there's less rest mass, but there's some additional potential energy that makes up for the difference between the 2. And if I imagine somehow that clip gets released, the clip that's holding it compressed, what would happen? Well, that spring would uncompress Those particles kind of really wanted to get far apart from each other because they had a repulsive force, but something else was holding them together. If it gets released, what happens afterwards? Well, this is what we'd think of as sort of like a nuclear decay, right? Something that I thought was one thing ends up shooting out two particles at high speeds, right? That's not like a nuclear decay. In this case, the rest mass, I would say, in the process of going from this particle here to this case over here, if I add up the rest masses, the rest mass decreases. The total energy is conserved in the decay. So I would say I have the same amount of energy before and after. Before I just had rest mass, and after I have less rest mass, but I have more kinetic energy because these things are moving. They have kinetic energy. And the potential energy decreases by the corresponding amount, okay? So however much the potential energy goes down, there's less energy stored in the spring, essentially none here, then the kinetic energy must go up to make up for the difference in rest masses there, okay? And therefore, just to kind of put it in a nutshell, we could say a change in rest mass, in this case, we started out with more mass over here, we ended up with less mass, but the difference is made up by some kinetic energy, results in a change in kinetic energy. And so we can say the change in kinetic energy in this decay is given by the negative of the change in mass times c squared. Right? This means the total, add up all the total masses and see what the change is in that case. So in this case, the change in, physicists and mathematicians denote change often by delta. So this means the change in mass. In this case, we would say the change in mass is negative because I started with more mass and I ended up with less mass. The sum of these two masses is less than the mass of this one. So delta m0 is negative itself. When I put an extra minus sign in front of it, that becomes a double negative, which is positive. And so the change in kinetic energy is positive. I end up getting kinetic energy out of it. It's like a nuclear decay. What that means is if I have an unstable nucleus, it's kind of like the constituent parts of that nucleus want to get apart. And if it spontaneously fires apart, we end up with a little bit less mass, but a lot of kinetic energy. And that kinetic energy can be used to heat up water and boil water and turn a turbine and power our electric grid and all that kind of stuff. Okay, so if we imagine, this is just a sort of a cartoon picture, but we can imagine that that happens. Now, why didn't we ever notice the difference in masses before? In other words, if I actually connect two, kilogram masses by a fairly hefty spring and clamp it in the closed position and then let it release and I measure the mass differences, I'll never notice the difference. Why is that? Well, in terms of the numbers here, the difference in the change in mass, if you look at the sum of these three things has to be equal to this one. The change in mass is related to the change in potential energy. That makes up the difference. And therefore, the change in mass from before the decay to after is the change in potential energy over c squared. Now, again, c squared is a huge number in normal units, right? 3 times 10 to the 8th squared is 9 times 10 to the 16th. And that means that the change in potential energy has to be huge in order to make this a noticeable number, right? Change in potential energy in normal units has to be like 10 to the 16th, or at least on that order of magnitude. Okay, so that means it's going to require an extremely strong force that is compressed a lot, right? We've got something like electrons that repel each other. You're going to have a really strong force that you've compressed a lot in order to store that much energy in that spring. Well, the force we're talking about here for nuclear decays is called the nuclear force, but sometimes people call it the strong force for exactly that reason. The forces that bind together nucleons into a nucleus are extremely strong, and they can store a lot of potential energy in them, but still allow for a decay. Okay, so that's what's happening in this case. In this case, it's sort of the opposite in that these 6 protons, 6 neutrons, and 6 electrons don't so much like being apart from each other. In other words, the electrons want to be close to the protons, and the whole thing kind of likes to be together. This is a really stable nucleus. Carbon-12 is almost all the carbon, and carbon doesn't decay. Really, carbon-12 doesn't decay anyways. So in this case, we have to add energy to pull it apart into its constituent parts. So if I pull this apart into electrons, protons, and neutrons, I end up adding potential energy into it because I'm like stretching springs as I pull those particles apart, and we end up with more rest mass afterwards, or if we consider all of these separately, we end up with more rest mass. Okay, but the opposite happens when we consider an unstable nucleus. If an unstable nucleus breaks into pieces, we actually lose mass when it goes from the whole thing to its pieces, and therefore we gain some kinetic energy out of it. And now, you shouldn't think it when an unstable nucleus breaks into pieces, it doesn't break into all its individual protons and neutrons and electrons. Nothing ever does that. You'll always gain mass in this table when you do that. But you can lose mass. Sometimes it spits out a helium-4 nucleus or helium-4 atom, essentially, and the rest of the nucleus stays intact. And you get less rest mass afterwards than you had before, the difference being made up in kinetic energy. All right, let's talk about some more visual, rather than concentrating on the formulas, visual ideas about microscopic versus macroscopic views. Again, here I'm imagining, here's a particle. I can't really see what's going on. It looks like a point particle, maybe like a little BB or something like that. It's made of some material, but I'm not paying attention to it. For all practical purposes, it is a tiny point mass. Now I zoom in. Maybe I zoom in so much that I can see the motion at the molecular scale. And I say, oh, it's made of all kinds of particles, and they're moving around. They all have forces between them. So when they come together and they're repelling, they store potential energy in them. And when they're moving, they have kinetic energy too. So I would say, in this case, from this point of view, well, there's just rest mass, and there's a certain amount of energy associated with the rest mass. In this view, there's the same amount of energy, but there's less rest mass. If I add up the masses of all these constituent particles, it's less than this one particle's rest mass over there. But the difference is made up by the kinetic energy, the motion of these particles, and the potential energy. At any one time, maybe there's lots of compressed invisible springs in there. Okay, so what that means is, if I can increase the rate of motion in here as I heat up a solid object, as I heat up my BB that look like a point particle to begin with, you've increased its rest mass. In other words, if I consider the BB, it has a certain rest mass, and then I imagine the microscopic view. When I heat it up, lots more motion, lots more energy stored in forces on average because they're bouncing even closer to each other. And so that means I've increased the amount of energy. And then when I view it again as just a single particle, the rest mass of that BB has gone up. So when I heat up a BB, it actually increases its rest mass. And you might say, well, oh, that's just, some trick of the mathematics. No, experimentally, you can find it actually has more inertia. It's harder to change its direction. So its mass in all experimental aspects behaves greater. It exerts a greater gravitational attraction. So if you put it on a scale, it actually weighs. You have to have a very sensitive scale. But if you heat up something, it weighs more than it does when it's cold. Okay? Okay, so let's just look at some notional pictures. Any way I can increase the potential energy or kinetic energy of something, if you view it just as a single particle, you'll think of it as having more mass. So in this case, here's a spring, totally relaxed, uncompressed, and I've got a little clip over here. And I imagine I come by and I compress the spring and put the clip on it, so it's stored in this compressed situation here. Now I've got the same constituent particles making this up, and I'm going to imagine I haven't changed the temperature in that process at all. In this case, because I've got, the only difference is that I compressed the spring, I've got more potential energy in that case. And what that means is if I view this as a single particle, I have something with less rest mass there and greater rest mass over there. Okay, in every respect, it behaves like it has greater mass. It really does have greater mass if I think of it as just a particle. Okay, here's a baton just sitting here. It's just not spinning, less rest mass. If I think of this as a single object, it's just sitting there. Now imagine I spin that baton at some great speed, so it's spinning around. I haven't really changed the potential energy, but I have changed the kinetic energy. There are little bits of mass now moving, so there's a lot of kinetic energy. If I envision this as a single particle, right? I zoom way out and I just say it looks like a single particle. And I investigate its mass, I would find out that this one has a greater experimental mass in every respect, and this one less mass. Now, the differences are tiny at the ordinary scale, so that would be difficult, but in principle. And same thing with heating something up. If I've got a chunk of cold stuff, I heat it up. This chunk has greater rest mass than the cold chunk. Okay, here just to test our understanding of this, here's a voting question. So you can hold up 1, 2, 3, or 4 fingers. 2 positively charged spheres that electrically repel. Maybe this is 2 protons if you wanted to imagine something fanciful. But we take 2 little tiny spheres, charge them both up positive. Like charges repel, so they want to get away from each other, but there's some little hook that's keeping them hooked together, okay? So this string they're connected by a piece of string, but the string is just sort of dangling there. And there's a hook, we can't see it, it's too small to see in this picture, keeping them from getting apart. I come by and I carefully unhook that hook and I let them expand so they're farther apart. And then I let go of it. That's the second picture in there. That's B. If we conceive of the entire thing as a single object, in which configuration does it have a greater rest mass? A, B, or they're the same, or I haven't told you enough information? Keep forgetting where the camera is oriented. What do you guys think? If you have an answer, hold up 1, 2, 3, or 4. You just survey the room. Okay, there are 1s and 2s that are here. Anybody want to argue strongly for A or B? Jack?
So if you let things come to rest gently without just taking the clip and letting it go, you're taking energy into your hands or whatever you're letting them come to rest gently.
Yes, so Jack is saying if I let that invisible electrical spring decompress, there's less potential energy stored in the force between the two. And I've got the same constituent particles here, so presumably their rest mass hasn't changed. The only thing that's changed is that the potential energy stored between them got less. And I'm saying the temperature of everything's not changed in the process. It's in all respect the same, except that I've let them go to that farther position there. And that means I've got the same sort of rest mass of the pieces, but there's less potential energy. So if I consider this as a whole, I would say I've let some potential energy get out of the system, and therefore this has less rest mass. This has a greater rest mass there. So A would be the correct answer there. Everything is the same except potential energy decreases, and therefore at the microscopic scale, we have less energy. So at the macroscopic scale, when I just consider it as a piece of mass, so small that I can't see it, I would see the rest mass has to decrease because it's all, all the energy is due to rest mass in that case. Okay, I know this is a lot for one day, and we're getting close to sort of all the punchlines I wanted to make. Rest mass you can think of because how much rest mass I assess there being in a certain situation depends on whether I look close or far away, right? Whether I have a coarse grained view or a fine grained view. Means that you can think of rest mass as not really a fundamental property of anything, but kind of an effective measure of the amount of energy present, right? If I say, hey, in this region of space, I may as well treat it as a point mass, but maybe there's some microscopic structure. But if I treat it as a point mass and I say the energy stored in here is m0c squared, that m0c squared is going to include all the kinetic energies and the potential energies that I would see at the microscopic level. And so the mass sort of just, this assessment of the mass by seeing how much inertia it has, how much gravitational attraction, it's sort of a way of taking into account all of those energies that are hidden at the microscopic level. They all come into this effective mass, okay? So you might think, here's an object that has it's just a point object with a certain mass. I look close, there's actually a bunch of things moving. If I add up their rest masses, it's less than the mass of this object, but the difference is made up by kinetic energies of those objects and the potential energies of those objects, okay? This is good because that means relativistically, if you can't see what's going on at a microscopic scale, it doesn't affect your assessment of the energy present, right? I'm not going to be surprised when I see this if I know about relativity and E equals mc squared, because I would say, you know, if it's a present there, it's going to affect the value of the rest mass of this thing. And that's not true in Newton's world. In Newton's world, if you imagine, because rest masses always add up, right? The sum of the parts is equal to the mass of the whole. When you have a mass, and I think of it just as a single mass, and later on I see it's made up of pieces, the sum of the masses of those pieces should add up to the mass of the whole, but there's some, in addition, some kinetic energy and potential energy I've discovered. So Newton's always saying, well, I'm not really sure how much energy there is in a system. There might be more hidden at a smaller scale, but I can't see it. Whereas for Einstein, if you can just measure the rest mass of an object, all of that microscopic structure is just kind of effectively treated as appearing in the rest mass. And so you aren't deluded about the amount of energy that's in a system, okay? So Newton, the point of all these words is to remind me of what to say here, because I haven't practiced this too many times, but an increase in your assessment of the total energy present as you break things apart into pieces and you find, oh yeah, there actually was some motion stored at smaller scales and I couldn't see it before. Okay, last couple of ideas here. What about the energy of a photon or a light pulse? We've been talking a lot about light pulses. They're a special case here, right? They're not like a massive particle. Light doesn't seem to have any mass, and in fact, photons and pulses of light, you know, are usually treated as massless kind of phenomena. If we look back at this formula for the total energy of something, well, it seems to not make any sense because the rest mass of a pulse of light should really be 0. But light also travels at the speed of light. And so when you plug V equals C into the gamma formula, you get infinity, right? Gamma goes to infinity as V goes to C. So a light pulse travels at C through empty space. That means this is infinity and this is 0. And if you know some mathematics, you know that doesn't, you can't really figure out anything from that. It's like, who wins, the immovable object or the irresistible force? Well, there's no good answer to that. And so that's just an indication that this formula isn't going to be really useful, and we need a more general formula that is going to be useful for photons. Photons do carry energy, but the fact that they have 0 rest masses causes problems for that formula. If we combine together, you know, start with this formula, and I square both sides, and it's not obvious from just looking at these formulae what you would do. Square both sides, and then I use the definition of momentum as gamma mv, and manipulate the right-hand side a little bit. You can derive this other formula that says E squared, okay, the total energy of a system squared, I haven't specified whether it's massive or massless yet, is equal to P squared C squared plus M0, that's the, you know, rest mass of the system, squared times C to the 4th. And now this formula we can apply to a photon because a photon has 0 rest mass, which means this term disappears. It goes to 0 if we're considering a photon. And then everything left that is squared, so I can just take the square root of it. That means E equals PC. And that means a photon or a pulse of light actually does contain some energy, and it also contains momentum. You may not think of a pulse of light as containing momentum, but you know, one of the ways that you can assess whether something has momentum, right? If you throw a basketball at my chest and it hits me, right, and bounces off me, it transfers some momentum to me and it sort of knocks me back a little bit, right? It's the same way with individual photons or pulses of light. If you shoot a pulse of light at something, the amount of momentum is pretty small for a typical pulse of light, but it actually does knock the thing back that it runs into. And you can generate machines that, you know, turn wheels based on this just by shining a light on them. Some of you may have heard those, you know, how are we going to get things to travel to distant planets? One of the ways to do that is to have a big sail that reflects photons from the sun. As the photons come in and bounce off that sail, they accelerate it faster and faster and faster. If you're out in empty space, you don't have any air resistance, right? So photons and pulses of light contain momentum. And so this is saying, you know, if it has momentum, it's also got some energy associated with it. And so pulses of light have energy, yes, even though they don't have rest mass.
So I have from the equations at the beginning of those slides that the momentum is gamma mv.
Yes, here's the relationship right there, yes.
So he said that photons don't have mass.
Well, yes, that's true. So what I'm saying is the photons don't have mass over here. What I'm saying is square both sides of this. It's not obvious. It's not just a couple of steps, but if I remember correctly, you have to work on it a little bit. Square both sides of this. Both of these equations are problematic for photons, right? Because there's an M0 in there. But let's just square both sides of this and then try to re-express what's on the right-hand side in terms of the momentum. And you'll find that you get this relationship where there is still a rest mass expressed in it, but if it goes to 0, it doesn't cause any problems. Whereas it definitely is causing problems here because it's multiplying a gamma, which is going to infinity, and it's causing problems over there. So we can get this relationship where M0 going to 0 just means that E equals PC. Okay. Here's just a couple last things. We're almost done with this. I know it's kind of a heavy lift doing all this stuff today, but here's an interesting possibility. Since the amount of mass I assess as being present in a particle or in some system depends on my perspective, maybe there's fundamentally no such thing as mass. In other words, I may say, oh, I found this thing. It's got a certain mass. The energy present is m0 times c squared according to Einstein. It's definitely got mass. But then you might do some experiments and look really close. And what you find at a really small scale, you might find that this consists of some massless particle. So I'm imagining this is a massless particle. This is a massless particle. They have a force between them that's keeping them attractive, and they're moving. So there's potential energy, there's kinetic energy there. But if I look at the constituent pieces, it's made of two things that are massless. So if I look at the microscopic scale, say fundamentally there's no mass. There is energy because those things are bound up in a way that has energy, just like a photon. Single photon can have energy because it has momentum. It can have energy. So this is, you know, you can actually produce things like this. I can't remember if I think people have discovered what's called a glue ball, but if you're a particle physics person, gluons are kind of similar to photons, but instead of being associated with the electric force, they're associated with the nuclear force. They're massless particles just like a photon. And yet you can get a collection of gluons that are all attracted to each other, and they're sort of orbiting around each other, kind of like electrons orbit around protons in a hydrogen atom or something like that, right? It's called a glue, that state is called a glue ball. But if you look at the constituent pieces, there's no rest mass there. So I might say every time it's possible, I don't know that anybody's ever come up with a consistent way to do this, that anytime we think something has mass, that's just an effective way of looking at it. But if you pulled it apart enough, there wouldn't be any mass. The mass is just sort of a placeholder for energy of motion that we haven't discovered yet for something like that. It's kind of an interesting possibility. So in terms of philosophical language, so people have mentioned the word constructivist sometimes. Or, you know, we might say this concept of mass is really constructed out of the associated notion of energy. No mass really exists, but mass is constructed or understood in terms of fundamentally massless things in motion. It's a possibility, consistent with what Einstein tells us. Although, you know, I should say, things that we attribute a mass to, like a proton or an electron or even individual quarks, there's no explanation for how those could be thought of with our current knowledge in terms of fundamentally massless quantities. So those are still stuck in our most current theories that are experimentally verified. Okay, so just to summarize the last couple of slides, any system that loses energy loses rest mass when conceived as a whole. If I come in, here's a, you know, ridiculous picture, but here's a mass that's at the top of a tall ladder. If I come in with my hand from outside the Earth, and take that thing and place it at the bottom, and I don't change the temperature, so we don't have to worry about all those kinds of effects. And then we go way back away from the Earth, and we just treat this whole thing as a single mass, and we do very precision measurements of the mass. I would find out that this has a bigger mass, right? Because there was some potential energy here that got smaller in this case, and therefore this has a smaller mass. So as you lose, any system that loses energy, in this case potential energy, loses rest mass. And we can see that in both atoms and nuclei that decay. So I'm hoping everybody's seen sort of this cartoon picture of an atom. This is supposed to be maybe like a hydrogen atom or something like that. And here's an electron in an excited state. Here's the ground state, right? We've all seen these kind of cartoon pictures of an atom before, okay? And you've probably been told, if something's in a couple excited states up, it can jump down to the unexcited state, that ground state, as long as it emits some radiation. It emits what's called a photon. And the photon has a certain characteristic wavelength associated with the energy that it has. So this atom had some extra energy stored in potential energy, right? This electron would really like to get close to the positive nucleus down here. It's far away, but when it does get closer, it loses some potential energy. That means there's some extra energy that's left over, and in this case, it gets carried off by a photon, a burst of light that gets sent away from it, okay? And that means that actually this atom is losing mass. Energy is actually conserved, but if you just look at the atom has more mass here and slightly less mass here, the difference being carried off by the photon, which just ran away with the extra energy that we had, okay? Okay, but I should say, in an atom, the difference is way too small to detect because the force associated between the electron and the nucleus, even though it is really huge, it's not big enough to actually, that difference in potential energy still isn't big enough to compete with that c squared, so that's smaller. The nucleus, I remember learning about this in high school chemistry or something like that when you talk about the structure of the nucleus. The nucleus also has similar kinds of energy shells or energy levels, right? You can't think of it as a single electron going around. Of course, there are no electrons in the nucleus, but the nucleus can be in a ground state or an excited state. And so here I'm imagining that this nucleus is in an excited state. And suppose it spontaneously transitions down to its ground state, its most sort of relaxed state. So it was in a high energy state, and then maybe the nucleons can get closer together when they're in a ground state. When there's a transition like that, it's also true that a photon is emitted in that transition. Now that photon is super high energy. It's called a gamma ray photon in this case for nuclear transitions. And this photon has a significant amount of energy. And what that means is the change in mass between this state and this state is actually experimentally detectable. So you find if you have a nucleus in an excited state and then it transitions to a ground state and all the photons run away with that extra energy, and you measure the mass of all those nuclei after the fact, you'd find out that they actually have experimentally determinable less mass. And that's sort of like that example of the carbon-12 disparity in between the mass of all the pieces added together versus the mass of the whole. And that, I think, is all I have to say today. I had a second part to the worksheet, but I don't think I'm going to put you through it because that's sort of enough for today. It was, we have to use that table of the nuclides and all that kind of stuff. So let's call it quits there. And I'm really looking forward to those final presentations tomorrow. If you have any questions about those, we can certainly do that in office hours today. So if you want to talk about final details about your presentation, stay after and we can work on the final things, okay? If not, I'll see you in philosophy class. Yes. Oh, thank you for reminding me. Yes, I'm going to hand back the tests now. As usual, those of you who are zooming in, as usual, I haven't scanned them yet, but I will scan them when I get back to my office, your exams, and email them to you. And again, everybody, this was sort of the first exam. You guys scored ridiculously high. The second exam, I think you thought was more difficult. The grades were still reasonable. And this one, think that average was an 85 or 86%, so it's, you know, pretty high on that side. High was 100 on this exam, which is really amazing to, you know, when I take my own exams, I probably don't get 100 because you make a calculator error. You're kind of careless with a minus sign here. Even if you know everything that's going on, it's hard to get 100. You have to really stay focused. Okay, Casey's not here. Reed. Jacob Camacho's not here. Spencer. Jesse. Emily. And Joseph. I think that's it. And as I said, I'll post the solutions. No, I won't post the solutions because Muchiri still hasn't taken the exam. So I'm going to email it to everyone except Muchiri. So I don't share the solutions class-wide anyways. I'm just going to take his name out of the email distribution list and email it to you so you can check stuff. And I'm happy to answer any questions you have on it, of course. Okay. Lots of people still on Zoom. You guys, if anybody wants to unmute and ask questions, I'm happy to entertain those now. Again, you guys will get your, if you weren't here today, I'll try to scan the exams and individually email them back. You're welcome. See you guys later today, I guess. Jesse, did you decide if you're going to sign up for Physics 210?
Yeah, I think I am.
Good, good. I strongly encourage you to. Just, you know, I hate to see people close that door, and though it's possible to do it in a really compressed fashion, if you take it a year later, you do have to wait a whole year to take the intro course again. And so it kind of puts you a little bit behind instead of being ahead. If you're thinking of a double major, that's something you want options for when you take things. A lot of physics majors or math double majors, or sometimes computer science. That's another common one. I know you said you're doing math. That's one possibility, right?
Yeah, I just have to figure out if I take the 2 labs or the math. I definitely am planning on taking it because
Yeah, I think that's smart. Yeah, and check out the schedule too. I'm teaching one of the sections, assuming we have enough enrollment, but mine's a little bit weird in that it has a Monday, Wednesday afternoon lab. So you have to have the last 2 hours free on your Monday, Wednesday, Friday schedule, which is kind of restrictive. But we just ran out of lab space in Olin Hall. We didn't have, you know, for the number of labs we needed to offer, we didn't have another lab space on Tuesday, Thursday. All right. See you in philosophy. What's up, Yichen?
Yeah, I just got the question. So you need the list of schools that I'm applying and my personal resume as well?
That always helps. I'll certainly read it. I know Dr. Rodenborn's been reading through and giving you advice on your personal statement, so I'm not going to like try to give additional advice on it or anything like that. So don't rush to give that to me. The most important thing is that if you have December 1st ones, it would be really helpful for me to know those, so I'm expecting them in my email and I can get them returned promptly. And I think you said you are expecting at least 1 or 2 December 1st.
Yeah, I'm expecting 3 programs but from 2 schools.
Did you say 3 different ones?
Yeah, 3 different programs, but that's from 2 different schools.
Uh-huh.
So, like, do you need the list? Because I'm not super sure about, like, do you need my personal